Hello everyone, welcome back to the latest session. In the last two sessions, we looked at how much water to design for, and then we looked at the kind of quality of water that we want to achieve, right? So obviously now we are going to look at how to achieve the quality of water that we want to achieve. Let's move on. So water treatment. So plant requirement in general, ideal case, depending on how well you design it and the capital costs, you want to design such that even when one of your unit process, let's say sedimentation tank 1 is out of service, the other said there should be another standby sedimentation tank to be able to cater to the needs of the population. So that's what we have here. So ability to handle design flow, the design flow with one unit out of service. So typical water treatment plant layout, let's look at this. So here we are concerned about removal of turbidity and color from surface water. Why is this important? As I mentioned, depending on the kind of water intake, water treatment process will change. For example, if it's groundwater, the aquifer, groundwater subsurface aquifer or groundwater aquifer will act as a filter, right? So thus turbidity will be relatively less in groundwater in general, unless it has great levels of influence due to surface water or such, but rarely that will be the case. So then I will choose a different mechanism. Why? Because groundwater typically higher hardness, I will need to look at removal of hardness and such. But if it is surface water, typically turbidity will be high. Turbidity in the sense suspended particulate matter or such will be high. So I need to look at that. So in that context, I would like to mention again River Yamuna, right? We have plants or water treatment plants, huge water treatment plants, 150 million gallons per day or such, I believe. 1 gallon is equal to 2.3 or 2.7 liters. So you have these huge plants in Mathura and Agra. So one built earlier is based on the traditional technique, and we will look at that, I guess, later, or rather I want to mention that later. And the other one, they are using a wastewater treatment process based system to be able to treat this surface water. Why is that? Because River Yamuna, depending on when you sample, you are going to have BOD to be this, and maybe COD to be 70, 80 milligram per liter COD, right? And here the issue is, if you look at the dissolved organic carbon, it will be around what, 8 to 9 to 12 milligram per liter dissolved organic carbon. So it's almost, not almost, it's under the category of sewage, let's say. So that's why they were using MBBR, moving bed biofilm reactor based plant to treat the water and then supply it for drinking water. So that's the kind of process or different kinds of unique process that people have to employ based on the kind of water that they take. But that's a unique case. River Yamuna, though it caters to a large population, typically we have rivers too, and we are not going to have those rivers being as polluted as Yamuna, but that's something that I wanted to mention. MBBR, I think you remember I showed a media in one of the previous sessions, and that media will act as a surface for the microbes to grow on. That those microbes will degrade my organic content, which will lead to this high BOD. Okay, enough of that. Let's come back to this. In this case, I am just concerned about surface water, which has relatively high turbidity, right? So what is it that I want to do? Let's go through stepwise. So surface water is coming in from stream, river or lake. Screens, right? You are always going to have screens because you will always have different kinds of stuff thrown into the water, and you can have a coagulant added. Yes, we will look at why a coagulant is required. We will look at that later. For mixing it well and for coalescing the particles and so that the initial coalescence starts, you are going to have rapid mixing, and then you will have a flocculation basin where you want to form the flocks. So here the turbulence and thus the mixing intensity will be less. Once the bigger flocks are formed, you will have a sedimentation basin where we use gravity, let's say, our friend, to be able to remove these bigger particles or bigger suspended particles or the flocks from the water, right. And obviously here we are decreasing the turbidity. Those particles that are too small to be settled out, what do we want to do? We want to form flocks. To form flocks, we want to see to it that the particles come together, but typically, they need to overcome their force of repulsion. So for that we add coagulant. We will look at the relevant reasons later, and then after that is done, the flocks can be formed, right. And once the bigger flocks are formed, they will be removed in the sedimentation tank, let's say, right. And after that, even then, you will have some particles which will still be suspended, but might take too long to be removed in a sedimentation tank. So you will have a sand filter, and in sand filter itself, you will have quite a few pathogens that can be removed, let's say, right. And obviously the last step is always disinfection. You want to kill the pathogens that are left, and that's why you add pathogens. Not pathogens, pardon me, you won't add pathogens. You are going to disinfect the water by adding a disinfecting agent, which is typically an oxidizing compound or UV, right. Why UV? It will damage the DNA or the RNA of the pathogens. And then we are also going to ensure residual chlorine levels or residual disinfection levels, so that in the distribution system you have chlorine that can tackle or take care of any microbial growth or re-entry into the distribution network. And what else? So from time to time, obviously these filters will be choked, so you want to have to backwash it, backwash. So if during the screen solids are formed, you have to dispose them. And sedimentation basin, the sludge that comes down, right, you are going to have to dispose it, typically inert if it's surface water. So this is the case. What is it we are doing here? In all this process, we are forming bigger particles, flocks, right, and then we are removing them from the water by letting them settle down. Here we are filtration, right, rapid sand filter, again suspended particle, right, and then we are killing the pathogens. So in effect, here we are removing the turbidity, and here we are dealing with the pathogens, right. So that's what we have. But if it was groundwater, which has hardness is due to calcium and magnesium. We will look at this again later, but just an introduction to help understand the issues. So this will affect, I will get pictures later at least. If this is my pipe, almost this section will be scaled up. For example, you would have seen this earlier, at least when we used to boil water for, I guess, hot water, to have a hot water bath or to drink, right. One sure way of disinfection is boiling the water. To drink, we used to see that over time this vessel had scale being formed, and over time I had to supply energy at a greater intensity or heat the water for a longer time to be able to achieve the same level of final temperature. So obviously my heating efficiency is decreasing there. And why is this due to? It's because precipitates of calcium and magnesium precipitation. Earlier they were dissolved in the relevant solution. When I heated it, some of it, some forms will precipitate out, right. So again, we have permanent and temporary hardness and so on based on how they can be removed, but we will look at that later. And what else other than this precipitation? Calcium and magnesium, they will affect the ability or the amount of soap I require to be able to clean myself, the utensils or the clothes, let's say. So that's again one other aspect. It will stain all your bathroom, where like pipes and such, and they will break. So these are aspects that need to be considered. Thus, we need to remove or look at removal of hardness. So groundwater from wells, so we can add different chemicals like lime or soda ash, lime CaOH twice, soda ash Na2CO3. So here we are adding lime to increase the pH, here to add CO3 2-, so that you can precipitate the compounds in the form of calcium carbonate or magnesium carbonate and such. We will look at that later, right. And then we are mixing that pretty fast, rapid mixing. And then we have the reaction basin here, right, and then the settling tank, we are letting that settle down and the sludge will be taken out, obviously settling down. and because the pH is being increased, you want to decrease the pH. How do you decrease the pH? By adding carbon dioxide. So, I think in this aspect I will need to look at the, or again briefly talk about acid base chemistry, because that plays a role, and then it will be easier to understand the relevant aspects rather than looking at it in what do we say, pieces. For example, carbon dioxide is a gas. When I dissolve it into water, right, some of it will dissolve in water, but it won't stay as CO2, it will stay as H2CO3, right. H2CO3 obviously has this 2 protons H plus, so it can donate that, it can donate H2CO3. So, H2CO3 will be in equilibrium with HCO3 minus and CO3 2 minus, right, and in each process it can give out 1 H plus. If you see, we are having acid dissociating. So, this is the acid and this is the most deprotonated form. For example, earlier too we looked at this HOCl being in equilibrium with OCl minus. So, this ratio of HOCl to OCl will depend upon the pH and pKa of the solution. We looked at that earlier, but we will come back to that. Why is that relevant? Because CO3 2 minus will precipitate out some of the calcium and the magnesium. That is why you need to add CO3 2 minus. At least that is what we are adding here. And here we are adding CO2 to bring the pH down, because during this step we increase the pH a lot. High pH water we can't drink. So, we are going to add carbonate to also increase the alkalinity and decrease the pH, right. That is what we have. And then again rapid sand filter, finally disinfection, storage and distribution, right. So, different ways to go about it. So, when we say you are drinking water, treat it, how are you going to treat it? It is going to obviously depend upon the kind of water that is being treated. So, unit operations, different operations that we are going to look at in this particular class or during the other half of this course. So, preliminary treatment we will not discuss much, but in general it is screens, right. And what else? At least in Agra and Mathura, what do they do? If they directly have these sedimentation tanks and such, microbes grow all along the side walls, or there is microbial growth. Why? Because there is a lot of organic content. Wherever there is organic content, the microbes will thrive. So, sometimes they pre-chlorinate the water. So, that is one kind of preliminary treatment, let us see. Another case is when you have high iron content in your water, let us see, right, Fe2 plus or manganese or such. So, you want to precipitate that out. How do you do that? Iron in the form of Fe2 plus is very soluble, meaning it wants to stay in water. But if you oxidize it to Fe3 plus, right, so how will it go? Plus electron, right, or if you see to it that the electron is removed, then Fe3 plus will typically precipitate out as FeOH thrice the solid pretty easily. But how do I do this? To do this, I need to accept this electron. So, what is a common electron acceptor? Oxygen is a common electron acceptor, let us see. Anyway, we are not going to balance it now. So, that is how you can go ahead and do that, as in you are going to aerate the water so that iron is oxidized to Fe3 plus and precipitates out. So, these are some of the preliminary treatment steps that are used, but we will look at that later. But we are typically concerned with turbidity or suspended particles, and relatively heavier particles, they would come out, right, but there are some that will not. Yes. So, how do I take care of this? So, what do I need to do? I need to first understand why are these particles not coming together by themselves, right. If there are different particles, why don't they come together by themselves and make my job easier? First we will understand why, and then we will see how we can start this issue of coagulation, right, when we destabilize the solution. Right now solution is stable, as in the particles do not want to come together and settle out, they are very stable. So, coagulation, I am adding coagulants to destabilize the system so that the initial coalescence can take place. Let us see, initially the particles can start coalescing, or I want to be able to neutralize the charge on the colloids. Again we will see why, and then after this we want to promote formation of bigger flocks. Flocks we also came across in that wastewater secondary treatment. After biological treatment, the kind of microbes we want to form, they will settle down, right. So, that is something we looked at. So, over the next 2 or 3 lectures, we will be looking at coagulation and flocculation. Then we will look at softening of hard water. Hard water meaning the one that has calcium and magnesium. Sedimentation, we looked at it earlier, but maybe now we will look at the design aspects. Filtration, different types of filtration. Ion exchange, relatively recent one. And disinfection, I guess I should have also had RO and what do we see? Under nanofiltration, we will look at, under filtration, we will look at nano or ultrafiltration, right? So, these aspects we will look at. So, let us move on and look at the aspect at hand, which is coagulation and then flocculation. So, first, okay, application for removal, where is it coming into the picture, let us say, right. So, I have microorganisms that are suspended on the relevant or in the relevant water. I have turbidity due to relevant particles that are out there, the toxic compounds that are adsorbed onto these particles, and NOM. So, water, let us say I have a river water, and if there is a thriving system, aquatic system or ecosystem, or let us say there is a rain and it comes in contact with the dead leaves and plants, and they leach organic matter, right, cells, and that comes into the river. So, all this builds up and you have natural or otherwise you will have a lot of organic matter, and these are again, as you know, precursors to DBP. So, I want to be able to remove these, I guess, right, and how do I go about that or such. So, the first aspect is what are the characteristics of the particles that I want to remove, as in why is it that they do not come together by themselves, right. It is okay, I guess I skipped it a bit. First is, why can't I remove them easily? Because the size is too small, as you can see, 0.01 to 1, right. Some bacteria and certainly viruses are in this particular zone. They will not settle in your lifetime. Even these suspended particles which are relatively heavier, now you can see from which range they are visible to the eye. As you see, all this, they are not visible to the eye, right, or most of it here anyway is not very much visible to the eye. They too take their own time. So, you want to fasten the rate at which they settle down, right. To do that, there are different ways. One is filtration, conventional filtration by granular media. You can see that I can capture some bacteria and such, but viruses obviously are not going to be captured, they are much smaller. So, they will be removed during ultrafiltration or nanofiltration, but again that is a different aspect. So, here I am concerned about these suspended particles, right, and if I want to just use conventional filtration where the size of the pores is relatively bigger, or just sedimentation to remove these particles, what do I need to do? I need to see to it that bigger particles are formed from the smaller particles, but they will not come together. Why is that? Because they have a net negative charge. So, why do they have a net negative charge? Let us see that. They have a net, let us say this is my suspended colloid and it has a net negative charge, right. So, this negative charge will prevent these two particles from coming towards each other, right, like they repel, right. There is electrostatic repulsion. So, there is a predominant negative surface charge. What is that due to? For example, ionization. Again, it is acid base or based on the pH, right. So, based on the pH, HOCl can predominate or OCl can predominate, OCl minus can predominate. This has no charge, this has charge. So, it's here, these are dissolved compounds, but I am just using that as an example. For example, you have silica. Silica has hydroxyl groups on its surface, right. Here we are talking about Si4 plus sand, silica, right. And depending on the pH, the pH here we talked about the pKa and pH, right, depending in the acid base context. So, this is the case and this is pKa, this is the HOCl, this is the OCl minus. If pH is low, most of the acid is present as HOCl and very less is present as OCl minus, which has a charge. So, similarly here we are not talking about acids and bases, but still you have different groups that change charge depending on the pH of the water. So, here we have these silica groups which are pretty common, and they have these silica which has hydroxyl groups which are pretty common on its exterior surface. Depending on the pH, it can have a positive charge, no charge or negative charge. Typically, it will be in this range. Why is that? If you look at it, it is only predominant when pH is far less than 2. Point of zero charge is when pH is equal to 2 and when pH is greater than 2, and that is what most of our waters are, right, or that is where most of our waters are. So, it typically has a negative charge, right. So, that is one reason for a negative charge. Adsorption due to humic acid or natural color on the silica surface, or let us be concerned with humic acid. We know that water has a lot of natural organic matter, even 3-4 milligram per liter of DOC, that means there is a considerable amount of organic matter. In Yamuna it is 12 or so, so it is 4-5 times or 3-4 times, so that is pretty high. So, this NOM will stay on the surface, not stay, suspended in the water, that is one aspect. But if there are particles, the NOM, natural organic matter, will be adsorbed onto the particles. So, most of these particles which we are concerned about will have natural organic matter or organic matter adsorbed onto the surface. And we saw these, one general structure for this natural organic matter, I think when we are discussing about disinfection in wastewater. We saw that there are different functional groups and such which can release H plus and such, and most of them do release their H plus. So, that is why they have a negative charge, and this humic acid or the natural organic matter will lead to a negative charge on the surface. So, that is another thing to keep in mind. Another aspect is isomorphous replacement. For example, a metal in a metal oxide let us say, is replaced by a metal with a lower valence. For example, instead of Si4 plus, if it is replaced by Al3 plus, or Al3 plus is replaced by Fe2 plus, right, you will see that that metal oxide will have a negative charge, right. So, isomorphous replacement will also need to a negative charge. And structural imperfections, well, this is not as common as the other three causes. Bonds are broken on the edge of the crystal, and you typically, due to these imperfections, you can have electrical charge or negative charge. In general, colloids have a net negative charge, right, and so they can't come together. So, the solution is stable. So, by coagulation I want to destabilize this, right. Okay, I guess to destabilize it, what do? I need to see to it that they come together. To be able to come together, what are the forces that are acting there and such, let us look at it. So, we have what is called an electrical double layer, let us say, right. Unlike what we just mentioned, a dispersion in solution does not have a net charge, right. Why is that? Because this colloids which have a negative charge will attract a positive charged layer around it, right. So, positive counter ions, right, counter ions on and near the particle surface, and this layer is pretty what do we say, thin. It is only 0.5 nanometer thick, and it is of cation, meaning positively charged. They are bound to the particle due to electrostatic and adsorption forces, primarily electrostatic, let us say, right, negative charge on the colloid. So, that is why it is surrounded by these cations or positive charge. And also, even after this, you have a loose layer, relatively loose layer of positive and negative. I think we have a good picture later, we will come to that. That forms beyond this what do we say, Stern layer. The above one is called Stern layer, and this layer can be up to 30-90 nanometers thick and has a net negative charge, and all this is called a double layer, right. So, this is something we need to keep in mind. So, that is what we have here. So, we see the electrostatic potential here. In the first case here, we see the colloid at the innermost region, and then you can see the negative charge, right, negative charge here, and then you can also see the positive charge in this region, the positive charge which accumulate around the colloid because of the electrostatic force of attraction, right, and that is called the Stern layer. This is the fixed layer or fixed layer, right, or Stern layer or fixed layer, and around this you will have this diffuse layer, right. Around this you will have this diffuse layer, right. This is what we have, diffuse layer. So, again negative and positive counter ion and all that is fine. And here we have the bulk solution meaning in general the water or such, but this is the electrical double layer, right. From this particular, okay, let me draw it. So, all this is the electrical double layer, right. So, electrostatic potential, as we go closer, obviously it's what do we say, much higher, and as we go far away, it decreases. So, that is one thing to understand or keep in mind. And here we see something called a zeta potential. We will look at that, but note that it is the one that's relevant to the diffuse layer, let us see, right. So, zeta potential, let us see. Let us move on. So, here if a similar particle wants to come nearby, right, this net negative field and such will not let them come together. Obviously, as you see, you have this electrostatic force of repulsion, but we will come back to that. So, how do I, what do we say, see to it that the particles can come together? Before we look at that, we need to understand some other aspects. So, zeta potential, just a side aspect, the electrical potential between the shear plane and the bulk solution, right. So, thus you can measure from here, as in if I apply a potential negative and positive, the colloids which are negatively charged will move out here, and they will drag a cloud of particles, which let us say typically positive will be towards or aligned towards the negative charge. Again, from this I can measure the zeta potential, which we also looked at here, let us see, right. So, let me move on. So, particle stability. So, particles in the waters are stable, right, because there is a balance there. Why is that? We have two forces. One is the electrostatic force that repels, or electrostatic force of repulsion, and the attractive force, which is the van der Waals force of attraction, let us see. This we can't do much about it, and this is obviously something we want in this context, but we can do something about this electrostatic force of repulsion. Again, the particles with negative charge, the mechanism controlling stability, as I just mentioned, is the electrostatic repulsion, and let us just understand this. So, if this is it, repulsion will increase with okay, if this is repulsion, electrostatic force of repulsion, this is it. So, and this is the distance. As the distance decreases, this repulsion force will increase, let us see, right. Let me try to draw it with a better color. So, as I am coming nearer to my particle of interest, this is increasing, right. But what about this van der Waals force of attraction that we talked about? How is that going to help me now? So, even that will be depend upon the distance, but even more what do we say, solely. So, it will come into the picture only when they are close by, and more importantly it will have a remarkable effect, something like this, okay. So, the net will be a repulsion force when it is near, not near, let me use this color. So, the net, this is repulsion, this is attraction, this is due to electrostatic force, this is due to van der Waals. What will the net look like? The net will be like that, it is in general repulsion, here attraction, there repulsion, in general this, and then a steep come down. So, in the area above this green line, it is repulsion. So, when it is relatively far away or just about to come to the surface or near the surface of my particle here, it is repulsion, and only later when they are very close will the attraction take over. But because there is repulsion when they are far away or just nearby, they can't come together. How do I make them come together? I can see to it that this electrostatic repulsion is decreased, right. Let me look at that. We will just look at this curve and end this session for today. So, here is surface of particle A and surface of particle B, right. So, I have two cases, repulsion curve number 1 and net energy curve number 1 when no coagulant is present. So, what do I have here? Particle is 0, here 0. So, as I bring one towards the other, repulsion force is this, repulsion force is this, and where is my van der Waals force of attraction? This is my van der Waals force of attraction, which increases greatly if I am very near. If I am very near, you see that it is remarkably high, right. But the net is somewhere here, and as you see, this barrier my particle can't cross. As it comes nearby, this repulsion will push it away. So, if I want to see to it that this repulsion is decreased from there to here, or if I can do that, then I see this net will be like this, right. as it comes nearer, you will have a net, what do we say, attractive, what do we say, curve or such, if I may say so, net attractive force. So, how do I do that? I can neutralize the charge on this particular colloid. So, that was what was causing this electrostatic, what do we say, repulsion. So, by adding a charge which is opposite to the charge on the colloid, I can cut down on this electrostatic force of repulsion. Then as the particles come together, the van der Waals force of attraction takes over and the particles can coalesce. So, this process is called coagulation. I am trying to destabilize the relevant system or the colloids by adding a coagulant here, right, and I am trying to trigger that initial coalescence of the particles. So, with that I will end today's session, and we will continue this in the next session. This in sense we will look at coagulation and then obviously flocculation, right. As usual, thanking you for your patience, I will end today's session.